Yeah, maybe do some research. Either.
Basically, that's the only thing. You're going to so much for unified.
Yeah, I saw it. Okay, fair enough.
Chuck, you ready? Okay. So, hey everyone, welcome. Today we have a couple of wrap-up things to do. So first I'll finish the D3 introduction. And then I will wrap up the data lecture. And then we'll get started on Marx and Chandler, the alphabet of visualization. Before we start, are there any questions about the homework, for example, or any other organizational things? Everybody is doing fine? Great. Cool, so where we kind of stopped last time was we had basic, we distinguished between, like we had D3 selections, and we talked about mapping the data, how do we handle elements that are added, that are removed, or that are updated. And so I'm gonna recap quickly what we talked about selections and binding data. So by using the select all D3 command, we can select on any element or on any class or on any identifier. We can also use any of these parent selections and so on. So anything that you could use for CSS selections, you could use in this D3 select or select all function. Like remember, the difference between select is only that the first element matches. So here, for example, a select on the SVG is fine because there's only a single SVG. But for example, we have multiple rectangles here. And so we do a select all. And then on the selection, so what this does is creates a data structure of these DOM objects. And then like an array of these DOM objects. And then here the data command binds the data to these DOM objects. So we have now the three rectangles that are in this SVG now have a data field associated with them of 127, 61, and 256. And then within D3, we have these chained methods. So like data here, again, returns an array of these DOM elements. An attribute applies something, but again, returns the array of the DOM elements and so on. But by doing that, we have this nice function of method chaining, so I don't have to do svg.data, svg.attribute, or rects.addData, rects.attribute, rects.attribute, and so on. So I can do this like simple chaining. And then all of these functions, many of these functions take either like an explicit value or also like a function, like an anonymous function where I evaluate some expression and then return the whatever I care about. So, and these anonymous functions, they then always have two parameters, the data parameter and the index parameter. By convention, they're called D and I, but of course only the order here matters. And so in this case, we are only using the index, like the position of the DOM element in this array. In this case, we are only using the data. And so this is where we do the data-driven styling. We here set a width of 127 in the first case, of 61 in the second case, of 256 in the second case, and the third case. So this is the basic idea. And then if I apply that, if I run that function, like remember this is this execute function that is being called when I click on the run button, then I get a bar chart like this. So then we talked about what happens if we have more elements than we have, when we have more data elements than we have SVG elements on the canvas. And if we don't take special care of that, we can see that the fourth element in the data array here is simply not drawn. And so how can we take care of that? Well, we have to separate this out into the enter selection. So here we're treating, here we are treating the update selection, and then down here we're treating the enter selection. Right? And you can think of this as like a set. So here we have all the elements, let's say, these are all the elements in the data, and these are all the elements that we have on the SVG. Data, and or let's say selection. Okay? So here are the elements where we have both data and selections. So that if you have 3 data elements and 3 rectangles on the screen, this is exactly this intersection, and we don't really have to properly, we don't have to explicitly treat an enter and update, and this an enter or an exit. So this is essentially the update selection. This here are the elements where we have data items, but not a matching element in the selection. So this here is the enter selection. Okay, and so this is what we're doing here. We're separating out the enter, like this corresponds to the set of elements where we have data but don't have a matching element in the selection. And then finally we have the exit selection here. These are the elements where we don't have data but have elements in our selection. So if I had, let's say, 5 rectangles in my SVG but only 3 elements in my data set, then I would have 2 elements in here. And so these 3 selections are what I have to treat separately, and this is what we're doing here.
Is there ever enter and exit?
Yes. Certainly. We're, for example, right now assuming that we don't care about which rectangle is which one, but next time we'll learn about how we can give each of these rectangles, for example, a specific unique ID. And so we could have, let's say, additional companies come in the chart and some of them dropping out. So it's very possible that you have all 3 of them.
Okay.
So here we're treating the enter selection separately by simply appending rectangles, but we're not applying the styling. And so what we see here is that we get the new element, but it is not properly drawn. And if we run this again, this is going to work fine because we already had the element in the SVG, and so therefore the element in the selection. So this is a way of fixing this problem. Here I'm simply copying most of this code here. This code here is copied down here, and so it's applied twice with exactly the same configuration, with the one exception that the new elements in the enter selection are green, the old elements are blue. This does work, of course, but it is not very elegant because I'm duplicating the code. And so the better way of doing that is by doing this piece here. Enter, append rectangles and merge selections. So what is going on here? We retrieve the selection, we select all rectangles and bound the data to it. So here we take the enter selection, in these enter selection elements, these are DOM elements that are not properly initialized, and by calling append rectangle, we make them to be SVG rectangles. And then by calling .merge selection, what we do is we now merge the update selection with the enter selection so that we are operating on this circle here. And this is the important part. Like we have like taken the uninitialized elements of the enter selection, appended rectangles to them, therefore made them initialized. Now we have these rectangles that are associated with data, and then we merge them with the update selection. And then I can apply anything that I want to do to those rectangles in one single place down here. And then this works smoothly as I would expect. So the same thing is of course true if I don't have any SVG elements. So here, like you can see, the SVG here is empty. I'm using 3 data elements. And in this case, I'm actually not doing the I'm doing the enter here. I'm not doing the merge just for brevity, but in practice you would probably want to do the merge. So this works fine. And so now what happens when we have more SVG elements? Then we have elements in the data set. So here we have only 2 elements in the data set. If we run this, we have this one leftover element because we're not treating this exit selection here. So this is not properly treated. And we can treat that by simply adding a very simple line down here, selection.exit.remove. And so by .exit we retrieve the elements that were not where D3 couldn't match a data element to any of the elements in the selection, and then we remove them. And so now if we do that, we see that this 3rd element is properly removed. So this is how far we got last time. This is like the fundamentals, and I hope that is clear. So if you have any questions, please feel free to ask. Great, so like, this is just a very basic, and if you get that, and if you reliably get that and understand that, then you will have, you won't have a hard time doing the homework. So here is now like some of the magic of D3. So we can do things like these dynamic transitions very easily. And so what happens in such a dynamic transitions, right? We have an interpolation between a previous state and a current state. So this is initialized with this like gray boxes, and then we want to run a linear or any kind of interpolation, if linear or nonlinear, for many different attributes. So we are actually interpolating here position, we're interpolating the size of these rectangles, and we're interpolating the color. So all of these visual attributes are dynamically interpolated here. And I actually did write that myself before D3 existed in OpenGL, and it took me like a week and a half or so to implement this properly. Now it's one single line of code, and it just works. So what are we doing here? All we need to do is call transition and then set a duration. So here, select all data and then apply transition, set duration to 3 seconds, 3000 milliseconds, and then simply keep doing our styling. And so this is then, we can see this is a 3-second thing here. If I reduce the time to 1 second, you will see that this is quite a lot faster. So this is all fine. Now we need to combine this again with the enter. So here I have 4 elements in the rectangle. I'm appending a rectangle. I'm appending the rectangle as red and in a static position and of a static size. Here I'm handling the exit selection by fading the element out. So this for exit selections is quite often quite a good idea to simply fade them in the background and then remove them. And so here I'm setting attribute opacity, like this is completely opaque. Then I'm starting the transition, set the duration to 3 seconds, set the attribute opacity after the transition to 0. So this is kind of the end state of our interpolation. And then once this is done, I'm removing the elements from the DOM. Because if I just set them to opaque, but not remove them, they would still be sticking around in the DOM, would just not be visible. Here we're merging the updated selections with the original selections so that we have this like circle that represents the data here. And then for the update we do some like simple transition for over 3 seconds. And then what we do down here is we start a second transition. So once this is completed, we start another transition for 3 seconds, but we delay it for 3 seconds and then we fill it to green and then increase the width. So okay, maybe let's look at this, what this all does. The red rectangle appears, it's moved over there, we're waiting for 3 seconds, things turn green and start to grow. And all of this is very simple to do, right? So we have simple, like here's a transition definition, here's a delay, and then we modify the styling parameter. Okay, so you've all seen this SVG path element, and so what we could do is we could simply like do this by hand. We would call SVG append path and then define the attribute the way we have learned it in the SVG lecture and the way you've used it in your homework with all these like move the pointer, then draw a line, and so on. So this works fine, but this can be of course a little bit inconvenient because these values here, they're like we want to draw these line charts in a data-driven way as well. And to do that, here's a simple example of how we can do that. So you will see that the result here is the same thing. We just take a little bit more structured approach here. So here we have points that have an x and the y value, the x-axis and the y-axis, and we store them in an array of points with an array of objects where we have x and y fields. And then we use the D3 line function. And the D3 line function, we simply say, we define for the line multiple x and y positions. And so this is very simple. We simply say .x is the data point .x, .y is the data point .y. So this refers to, like we're assuming that we get an object of this type here with x and y, and then returning those values. Of course, these could be arbitrary names, right? And so I could refer to them here. It's just convenient that they're also called x and y. And then we simply call, like here, we simply call the line function with the points as the path attribute. So this line function takes in the data array that we give it here, converts that into the path element, and then applies that. So this is simply, this generates this path element for us, and we don't have to think at all about how the SVG path element works in practice. So we can see that this is the result here. And we can also try out a couple of different interpolation techniques. So we've seen last time that we can do curves, for example. And so by simply changing that a little bit, we can get, in this case, I think we're using a cut-model curve, or we could use a curve. And then we can actually also change the bundling strength of this curve. So these are the kind of variations that you can do. Of course, like what is sensible for your design can vary a lot. Okay, so this was kind of like the wrap up for the D3 lecture that I couldn't finish up last time. Any questions about D3 before I move on to like theory lecture again? Okay, great. So in your next homework that will be released today or tomorrow, you guys will be creating a couple of bar charts using the D3 API, but also the standard DOM API, which we'll be talking about on Tuesday. And there will be some interactivity, so we'll be switching through data sets, and so you'll have to do proper enter updates and exits and so on. Great. So next, I wanted to quickly review what we talked about dataset types. So we distinguish between these dataset types, tables, networks, fields, and geometry, and we discussed them in some detail. I emphasize the value or the importance of the semantics. Only if we understand what things mean can we actually make sense of a specific cell or specific data items. So we need to understand the real world meaning. Then we distinguish between items and attributes, where items are these individual discrete entities such as patients, cars, stocks, cities, which are called independent variables, and attributes would be these measured, observed, or logged properties such as the height of the patient, the blood pressure of the patient, or the horsepower of a car, or the make of a car, which are commonly called the dependent variables. So here, like the people would be the items, and then we would have the attributes. These observed elements would be name, age, shirt size, and favorite fruit. For tables, we distinguish between flat tables and multidimensional tables. For flat tables, we have one item per row, and each column is an attribute. So this is kind of like what we've seen before. Here, the item, and then each column being the attribute. We have a unique key that can also be implicit, just the position of the row, but there is always some kind of key in a flat table. And then we can also have multidimensional tables where we have indexing based on multiple keys. So we had this example of the genes of multiple patients last time. Okay. We talked about graphs or networks, and then we talked about, like, we'll talk more about graphs when we talk about graph visualization. Then we talked about different fields, especially about these grid types, how these fields are sampled. Remember, the fields are these continuous data sources, and we have to somehow sample them. We have uniform grids, we had rectilinear grids, we had structured grids, and we had unstructured grids. We talked about geometry, which kind of defines the shape of the items by using explicit spatial positions, which are not really a core visualization topic, but we'll be encountering them when we deal with maps. And then we had other collections such as sets, lists, and clusters. Then we talked more about the attribute types, and here there's a couple of important distinctions. So there's the unordered categorical data, which is also called nominal data, where you only can compare equality. So there is no difference, or there's no orderable difference between apple or pears or peaches, or there is no orderable difference between a horror movie and a drama movie. There is, however, like categorical ordered data types, such as, for example, shirt sizes. So these are not, like, I can't say like a large shirt is twice as big as a medium shirt, but I can order them, I can make any assumptions about their ordering. And then we talked about quantitative measures, where I can do arithmetic, things like length, weight, and count. And then we distinguished interval types from ratio types, and the main difference here was, does 0 have a meaning? Is 0 equal to none? And if you actually have a meaningful 0, then you have a quantitative ratio type, and if you don't have a well-defined 0, such as, for example, in temperature or a year, then you have an interval quantitative data type. And so this is kind of like this table that sums this up. We have nominal data type, the nominal data type that only allows us to evaluate equality or inequality. For ordinal data, we can also define the order. For interval data, we can do additions and subtractions, and for ratio data, we can also do multiplications and divisions and express proportions. So then we stop with this quiz, and I think we didn't get to this point. This is kind of like the first new slide. We talked about, or we didn't talk about them. Let's think about sequential data. There is sequential data is homogeneous from a minimum to a maximum. So, for example, the number of people in a country, right? There could be a country with 0 people in there, but the country, like every country, has like a number of people in them. If we have there's no country with minus people. Like there's no negative number of people that you can't count negatively, right? For diverging data sets, you have essentially 2 or multiple sequences that meet at some kind of inflection point. So, for example, and a good example is an elevation data set, where I have elevation above sea level and elevation below sea level, so where there's water. And so here is a color scale that appropriately visualizes this elevation data set, but does not account that we have a meaningful 0 here. So this is a diverging data set. So this goes to minus 3,500 feet, from minus 3,500 feet to plus 1,000 feet, but it doesn't take special care of this neutral point of 0 here. And if we have a color scale that does take care of that appropriately, we can actually make sense of this picture. That is just a very simple example of why this is important. There can, of course, be other structure in your data set. So a good example here is cyclic data. Human life happens in cycles, right? We have days, we have weeks, we have months, we have years, and these cycles often have observable patterns. And if we leverage those cycles, the knowledge about those cycles, we can see interesting things in the data set. So here, for example, on the left, this is a data set about respiratory disease cases. And on the left, this is a 25-day pattern. And you can't really spot a clear pattern, but if you change the cycle here to 28 days, you can see a very clear weekly pattern. So like people go to the doctor for their respiratory cases usually on Mondays. So they don't usually go to the doctor on the weekends because the doctor is closed, because they can probably don't have to go to work anyways. These kinds of patterns, they are very observable. And then these patterns, they can also happen on multiple levels. So here is like a Google Analytics plot of this course website from a couple of years ago. And you could see that here in the summer, July, October, essentially nobody really looked at this class, and then the class started in January, and you can see on this course aggregation level, okay, around here was like a big spike. This was where the course website was actually in some newsletter and so on, and so that kept going. So this is the global trend that we see at this resolution. If we break this down to a daily use, we can very clearly see here the weekend. So this is like Monday to Friday, then Saturday, Sunday. Monday to Friday, Saturday, Sunday. This is the same time range. This is this peak here, but we simply cannot observe it in this aggregated resolution. So how you aggregate data depends a lot on what you want to show about the data, and you always have to be aware of these structures. Okay, so here, just an example to reiterate what we had in this lecture. This is the item of the table. This is a table of product orders. Like we have an order ID, order date, order priority, the product container, product base margin, and the ship date. So this would be the item or the element or the independent variable. This here would be an example of an attribute, which is also called often a dimension or a dependent variable, or sometimes also called a feature. Here we have the definition of the semantics. What do those things actually mean? Where are the keys here? Who thinks it's the order ID? You guys are wrong. The order ID is not unique. So in this table we have like one order can contain multiple items. But this is a table of items. So where could the keys be here? The first column would be? What's that? The row number, yes. So this is an implicit key here. So it is the row number. It's not the order ID. What are the attribute types? Like, is it nominal? Is it categorical? Is it ratio or interval? So what is the order ID? What's the attribute of order ID? What's that? Ordinal? Ordered? Are you saying ordered or yes? Anybody have a different opinion? Yeah, so you could make an argument that it could be ordered, but you could also say the number really doesn't matter, right? It could be a unique key. I wouldn't want to infer an order by that. What is the order date? Interval? Yeah, that's correct. What's order priority? Ordinal, yes. Product container. Categorical here. Any other opinions? So you could make an argument that it's either categorical or ordinal, right? Depending on how you think about it. The product base margin. Ratio, correct. Now ship date is order date. So here is just a distinction between like not interval ratio, just categorical, ordinal, quantitative. So here yeah, this is kind of like debatable whether categorical or ordinal. And these are, I would say, ordinal, but could also be categorical. Okay. So then I also wanted to emphasize this difference between like a data model and a conceptual model. The data model is a low-level description of the data where we also have operations defined. So floats, for example, with additions, subtractions, divisions, and multiplications. Whereas the conceptual model is really more about the mental construction that we try to infer on a data set. So here this includes semantics and supports reasoning. So for example, the data model here would be like 1D floats, and the conceptual model behind it could be temperature. Or the data model would be a 3D vector of floats. The conceptual model here could be space. So this distinction between like how it is stored and what does it mean is very important. So from the data model, so for example here we would have to a series of numbers like 32.5, 54, minus 17 are being floats. We can make sense of these values by using the conceptual model that these are temperatures to a specific data type. So we could define our data type to be quantitative, continuous to 4 significant digits, or we could bin it into multiple categories as hot, warm, or cold to be an ordinal data set, or we could infer from that like a nominal distinction between burned versus not burned. So what we collect in the data, we have to bring in semantics and reasoning about that, and then we very often have to transfer it to a data type that makes sense for a specific application. So right now we have thought about those things in these isolated silos. It was either a graph or a table or a set or a cluster or something like that. But in practice, these combinations are very common. So networks or graphs of people, for example, have attributes. Like every person in your social network has an age, an occupation, and other things. So there's both a topology and attributes about those nodes relevant. Attributes have hierarchies, so I can break down attributes into bigger classes of attributes. Data types can be transformed. And so kind of like the point of this slide is really just to say that these are sensible abstractions to think about for conceptually, but in real life we have very often combinations for meaningful visualization problems. So real life is complicated. So that concludes the wrap up for the data lecture, and now I want to continue with the Markson channel lecture. Okay, so let's do another little exercise. How can I visually represent two numbers, let's say 4 and 8? You'll be shouting out solutions and I'll be drawing. How can I show graphically two numbers 4 and 8? Okay, sorry. Yes?
4 sticks and 8 sticks.
4 sticks, like yes. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8.
Bar chart.
A bar chart, yeah. I could have something like this, and then something like this. About twice the height.
Number line. On the number line.
Number line.
Number line. Yeah. This. So what are we using here?
Final.
Position. Like this is essentially we have a reference point and then we have position at 4, position at 8. Yeah?
Area.
That's correct. Area. I could have like bubbles like that. Other ideas?
2 arrows of different lengths.
2 arrows of different length, yeah, which is related to the bar charts, right?
Pie chart, make it 12 parts.
A pie chart?
It's 12 parts, 4 parts, and 8 parts.
Yeah, so something like, okay, how is my like 12? It's like a third roughly, right? Something like that? Other ideas? Right now I'm only using a black pen. I have blue and red. Anybody suggestions? Okay, nobody wants to say color. Good. Yes?
can have 4 bubbles and 8 bubbles.
Yeah, which is kind of related to this up here, right? We have kind of some explicit counting, some isotype. So we could have like 1, 2, 3, 4 versus 1, 2, 3, 4, and then we could also do some smart grouping. So we see this is kind of like a duplication. Yeah.
Angles by ratio.
Angle.
Angles.
Yes, we can use angle. 4 versus 8. We could also, it's hard to draw, do like value. I'm just gonna do shading here versus something which is much more shaded. So this could be either texture or value or saturation. But clearly color is not a good idea for quantitative values. Any other ideas? I could use curvature, things like. But of course these get increasingly esoteric. So like, let's think about this in a bit of a more structured way. When we talk about the visualization alphabet, we distinguish between marks and channels. The mark here represents an item or links. So like each row in a table is represented by a mark. And then the channel, they change the appearance proportionally to an attribute or based on an attribute. So for example, if we have item person and height, and the person's height is what we care about, the attribute, then we would use, like for example, the glyph of a rectangle as the mark and the height of the rectangle as the channel. And and so this is like how we create these visual variables. Also note that in the literature you will find the words channels and visual variables used interchangeably. I also use them interchangeably. I'll try to use channel, but I've also used visual variable a lot. So these two things mean the same thing. So what are the marks for items? It could be like basic geometric elements, such as points or lines or areas. So here we have like, the marks here are these dashes, the marks here are the circles, the marks here are the rectangles, these areas, or here it's these points. It could also be like a line chart, for example, in some way. For 3D, you could also, like a 3D mark could also be a volume, but in practice this is rarely used. Marks for links show, like we talked about those when we talked about Gestalt principles. This is a little bit hard to see, but here is like an enclosure. Here we have an explicit connections, and here are a couple of other examples. So these are the marks that we use for the links. And then we can also use nested containment. So here is an example for a Euler diagram where we have like a multi-level nested containment. So this person, Sophia here, belongs to this dark orange group, the light orange group, the pink group, the other pink group, violet group, pink group, and to the blue group, for example. And then we have these vocabulary of channels or visual variables. They control the appearance, proportional or based on an attribute. And these are the ones that we came up with here. Things like position on like the number scale, or color, or shape, or tilt, or the length, or the area, or the volume. And of course, not all of them are equal. And this kind of like the systematic approach to this goes back to Jacques Bertin, who was a French cartographer who passed away in 2010. He wrote this very, very influential book, Semiology of Graphics, that for the first time like came to a structured approach to these visual variables, to these channels and marks. And so he developed these theoretical principles and also provided a ranking of them. And so this is what he came up with. Here we have the marks, points, lines, and areas. And then we have position, size, the gray value, texture, color, orientation, and shape. And so we have since like done very detailed studies, as you, like if you've read the paper, as you've seen, to understand which of these marks and channels is sensible in which situations. Okay, so here's an example of using marks and channels. Here in the first one here we have the mark being the line or the rectangle. The channel here is the length and the position. And what we're encoding here is one quantitative attribute and one categorical attribute. So the quantitative attribute is the magnitude. The categorical attribute here could also be the item, but could be something like Asia, Europe, and Africa. on this chart here. If we use as a mark a point and then channel position, we can encode two quantitative attributes and we get something like this scatter plots, and we can see the relationship between these quantitative attributes very well. If we then want to use an additional categorical attribute, for example, to again encode the continents that we had here, we can add, for example, hue, and then we have we can distinguish here, let's say, the European values from the African values. And then if we add another one, for example, to encode a third quantitative attribute, we could use size. And so like that, I could, in theory, keep combining these attributes and create these increasingly complex representations. Anybody can see a problem with that? Like what happens now if I add, let's say, volume or shading or anything like that here to encode more information? So these things are not independent, right? Like there is interactions between them. For example, if I have very, very small dots, I can't really see the color anymore. I'll have a better example for that later. We can also use redundant encoding. So here, I'm actually using 3 different encodings just to show one particular value. I'm using length, position, and value. So length is used by simply plotting these bars at different lengths. Position is essentially used by look at the position of the upper edge relative to the lower edge, which is a line here, and then the value of these bars also represents this data. So here I have a 3-fold redundant encoding, which can be very powerful, can also be problematic. So what's wrong with this bar chart? This was the Snowmageddon season in Boston. They had this interesting bar chart where before January 23 they had 5.5 inches, and then after January 23 they had 71 inches. So what's wrong here? This is absolutely not proportional, right? There's completely different scales for those bar charts, and I actually don't get the point here, because usually newspaper or news organizations try to make something more dramatic, but here they're actually making it less dramatic, right? It looks like, oh, we only get an extra 20% of snow, but in fact it's many times as much snow. So I don't really understand what is going on here. So the one rule is to use the channel proportional to the data, which is kind of obvious, but you would be surprised. So we distinguish 2 different types of channels. These magnitude channels, we can use them for ordinal and quantitative data. They let us express quantities, how much, and the good examples are position, lengths, and saturations. And then we have identity channels that simply allow us to keep items apart, but cannot convey numerical values. And so what these are, for example, shape, color, or also spatial region. And this is applied for categorical data. And this is from our textbook that we used by Tamara Manzner. This is this order table ranked these various channels for magnitude and for identities, ranked by effectiveness. And this is of course based on studies such as the one we've just read to come up with those rankings. So position on a common scale is the most powerful scale, the most powerful channel for quantitative, for magnitude channels. Position on an underlined scale is the second most powerful. Length is the third most powerful. Then we have tilt, angle, area, 2D size, the 3D position, color luminance, color saturation, curvature, and volume. For the identity channels, again, spatial region is very important. So we can separate things out. For example, everything of type A is on this side, everything of type B is on this side. But we can also use color, hue, we can use motion, or we can use shape. You basically see that there's a lot less options for categorical attributes. You kind of have to be a little bit careful about how to pick those. So in this example here, this is a New York Times visualization where we see the tax rates of various companies in the United States. So what are the visual variables, the marks and channels that are used here? Color? What does color encode? Please raise your hands. Color encodes
Value.
The value, well, can I be more specific?
The effective tax rate.
Exactly. So color encodes the effective tax rate, but can you distinguish between an effective tax rate of 3 and 5% by value? No. So color is used in a binned way. So there's a couple of bins, and it's basically they kind of like give us a hint of the overall average here is 29%, and so they give us like a hint of below average and above average. Which other marks and channels are used here? Like, what is the mark? How are the companies encoded?
The bubbles.
Yeah, now I'm looking for the mark, not a channel. It's just the circles, yes. So that's the mark. Companies are encoded by circles. And then the attributes of these companies, so for example, the tax rate is varied by what? We already had color, and which other attributes do we have?
Size.
Size, yes. And the size essentially tells us the market capitalization, how big those companies are. We can see that there's a couple of really big companies. Here's Apple, then here, let's say, this is Citigroup, this is Exxon, and so on. What else? What other channel is being used here? Location, yes. That's also position. And can you be more specific?
It goes from one side to the
Exactly. So we have an X position on an X-axis. Do you think the Y position is meaningful? Not really. Yeah. There is kind of like this is basically even. I'm even doubtful that the X position is precise because this is probably some force-based layout here, so that you should get a rough idea of where things are, but I'm sure that this is not completely precise, like to multiple digits. So the Y position here is kind of like more of a function of how many other companies of which size are in the same area. It doesn't tell us too much. Well, I guess it tells us that the majority of the market is somewhere in this area. Okay, and then if I click on this button here, now I'm separating it out by industries. And so what am I using here now? What channel? I couldn't hear you.
Category? Industry identity?
Yeah, so we were separating it out by industry, and how are we doing that?
X or the Y location.
By Y location. So here we're using a categorical variable encoded by spatial region. So we say the utilities here are in this area, the information technology companies are in this area, the industrials are in this area. So we're using like the categorical information, which type of industry is it, and plot that by spatial position, and then we use the actual tax rate also by spatial position. So this is a very effective chart. They use the most important pieces of information. They convey them with the most powerful channels. And I think they're doing a pretty good job with this particular chart here. Interesting to see is also like who's paying the lowest taxes, utilities, and the big IT companies. Like Apple is one of the like companies that barely pays any taxes. And if you look at the high taxed areas, this is insurances and energy. Like Exxon, for example, pays about 37%. And that of course means something if an economy like the economy of the United States moves more and more into this area of information technology and those companies are lowly taxed, of course this has implications for a nation's tax base. Okay, so great. So let's think a little bit more formally about the characteristics of these channels. So what can we say about those channels? We can say, are they selective? Can we easily distinguish marks from each other? So for example, if there's only a slight variation, if we use a specific channel, can we actually tell the difference? Are they associative? Does it support grouping? For example, if we have similar elements, can we perceive them similarly? So for example, here position clearly supports grouping. We have D3 elements that are similar and then D3 elements that are similar. And then are they quantitative? Can we quantify the difference between two marks easily? So like this here is about twice as big as this here. Can we order them, like this magnitude versus identity question? Can we see a change in order? And then length, and by length I mean how big is our span of things that we can make use of, right? We talked about that we can only use a limited number of color, but we can use a very broad spectrum of positions. So we can like have a table with many hundred rows, for example, and that works well. Okay, so let's review those. Let's review those individual channels. Position, as I already mentioned, is the strongest visual variable, and it's suitable for all data types. What are the problems associated with it? Well, sometimes it's not available. So for example, if you want to plot information on top of a map, you can't really choose your position because your position is given by the location, for example, of a city. And it can lead to cluttering. So for example, if I have densely populated areas, I have a lot of information in the same place, and then I can't really distinguish between those items. So they are selective. I can clearly tell them apart. They are associative, they support grouping. We can do, of course, quantitative data. They support ordering, and we have a pretty big vocabulary. They have a high length. So a good example here is the scatter plot, of course. Here the scatter plot shows us the income inequality between men and women. So you have men on the x-axis and women on the y-axis. And again, this is like an older New York Times chart, which is broken. So this is like one problem. Older charts used Flash, and now they're dying. So I'm curious whether this is going to happen with D3. Well, we still have the figure here. So we can see that there's only a couple of jobs where women actually make more than men. And I think this was nursing or something like that, if I remember correctly. And then there are certain jobs where women make about 10% less than men. And then there are certain jobs where women make more than 30% less than men. So this is, I think this is law or something like that. Position, as great as it is not as good in 3D. So for example, if you look at this 3D scatter plot, this is sales for over multiple years. And then cost. So we have the sales, we have years, and we have cost. And it's really hard to tell apart, like this here, like which of those, like where are those points, what are the exact values of those points, right? We have occlusion, like we can't really, for any of, like this yellow point, how many, like is it 25 or is it 15 in terms of sales, or is it 25 or 15 in terms of cost? So position in 3D is really weak, and you can kind of make this a little bit better by using interactivity, by letting people navigate and so on, but still it's not a great visual encoding because of all of these problems. So length and size of items, such as like the size of a rectangle, the size of a bubble, the length of a bar, are good for 1D, okay for 2D, so rectangles, for example, are harder to perceive than the length of a bar, and they're bad for 3D. The volume, we're really bad at judging volumes. Aligned bars, as I already mentioned, use position redundantly, so it's easier for us to make a comparison between those two, because here we're using position than to those two, because they're not aligned, and so we only have to rely on our perception of the length. They are selective, they're associative, they're quantitative, they're ordered, and we have a pretty high length. So they are generally like a good visual variable. So here is an example for using 2D size. This is like how, again, a New York Times graphic and how to slice Obama's budget. We'll be looking at this a little bit in more detail at some other point, but what you see here is essentially just the major expenditures in the US discretionary spending budget. So we can see Social Security, or it's actually all spending, not discretionary. Social Security and Health and Human Services here are by far the biggest blocks. Value, luminance, and saturation, they're okay for quantitative data when you can't really use length and size because they're used in some other way already. You can't really recognize very many shades. They are selective, they are associative, they are somewhat quantitative, but there are problems associated, so it's hard to judge whether this is twice as big as this, for example. They're ordered, and we only have a limited vocabulary of them, so we can do maybe like 8 or 10 different ones. So here is a good example of a diverging value scale map. We have like map. I like to think this is Obama-McCain election. And we have this map, and we not only show binary who has won that, but we also show by how much for each district in the United States by using this value scale here. And so you can see like that there are some like big counties here that just barely went to Obama, but that many counties, like, especially in the Midwest, went clearly to McCain. We talked a lot about color and perception lecture. Just think about it for a minute as a visual variables. It's good for qualitative data as an identity channel. We have a limited number of classes, as I already mentioned. We only can use about 7 to 10 different colors. It does not work with quantitative data, and we've talked a lot about the different pitfalls with color, so be really careful when you use that. So my rule here is to minimize color use for encoding data, used primarily for brushing, to also leverage these pop-out effects that we talked about, that we have like a clear distinction between a background and then one, for example, selected color. They're selective, they're associative, they're not quantitative, they're not ordered, and we have a very limited length because we only have 7 or 8 colors that we can use. So here is a terrible example of a use of color for a quantitative data set. This is estimated fraction of precipitation loss to evapotranspiration. If in this, like how much of the precipitation evaporates quickly. And this is this very, very complicated color scale where you have like different colors have completely different meanings, and it's not necessarily like there's no clear ordering between those colors. So if you're not trained at looking at this color scale, you might actually think that these dark values here, for example, are high, but they're actually pretty low, right? They're lower than the brown values down here. So there's no clear ordering. Experts still tend to like those because they are used to seeing those, but you have to really train to understand such a color map. So it's not easy to learn, and I would argue there's better ways of doing that. And I think I already showed this particular chart. This is a good example of the use of color, where I simply want to highlight one aspect. For example, here, this is the football, Peyton Manning's pass record. And the distinction that they use for color here is just like who are the active players. They want to emphasize those because they could, in theory at least, still beat Peyton Manning's record, versus everybody in gray is already retired. So this is like a great example of the use of color because it highlights one important point and it clearly pops out. So shape is great to recognize many classes, but unfortunately we have neither grouping nor ordering. So they are selective, but the associative power is very limited. They are not quantitative, they are not ordered, but we have a gigantic length. And so clearly there is no ordering between, for example, these 3 symbols here, but you probably recognize all of those symbols. So we have very, very many different symbols that we can use, that we can leverage. That is like great, but you also have to learn them, right? And again, there is no ordering, and it's hard to encode anything but identity to them. People have actually tried to use that to encode quantitative data. So this is an influential paper from like very early, I would say, visualization paper. And the theory behind that paper is that we as humans are really, really well trained to see faces, right? We can see very subtle changes in faces. So for example, these 2 faces here are only subtly different, but we can very easily make out that difference. And we wouldn't be quite as good if it were not some like facial glyph. And so the idea of this person, Chernoff, who was a statistician at Harvard, was to use facial parameters to map to quantitative data. So he would take 5 or 6 different numerical values and then map them to the distance between the eyes, the length of the nose, the curvature of the mouth, the curvature of the face, and so on. And so this was the idea behind that. Who thinks that works? It is really, really hard to see that. Like, it's clear for us that there's differences, but we cannot translate it back to the quantities that we want to represent, right? Like the eye size here is pretty big. Okay, we can make an explicit effort of thinking about that, but what other factors play a role in that particular phase is just important for us to see. So there's a link to a detailed critique on these general phases, because for a period in visualization they wouldn't go away, but now they have gone away. There are many more channels, right? There's this website here that shows us 45 different ways to communicate two quantities. So we could have, like, one thing that we didn't mention are writing or like just numerals, like either Roman or Arabic numbers. Here we have these squares, repeated icons, bars, line graphs, splice bars, and so on. So there's many more here, and some of them are really weird, like icon surfaces, volumes, special metaphors, and so on. So you can take a look. This is more like illustrative. This is actually an interesting one. This is Fat Fonts. Fat Fonts tries to like mix the numerical representation with the appearance. So like a 7 here appears darker than a 3. I think I have an example sometime later in the lecture, in another lecture. So I'll go a little bit more into those fat fonts. So why are those quantitative channels actually different? So it turns out there is some theory behind that. So first, Stevens has studied the relationship between the physical intensity of a stimulus to the perceived sensation. And so he has found that the only stimulation where the stimulation matches to the actual physical intensity, where we have a linear relationship between those, is length. And that's why length and position are these great visual variables. For example, for saturation, there is like lower physical intensity, but we perceive it too high. Electric shock is really a terrible variable to encode data. So small variations in electric shock are highly strongly perceived. So never use electric shock to encode data. Area, we tend to underestimate areas. We tend to underestimate brightness, and we tend to underestimate depth. And so this is like Stevens' psychophysical power law. This is like the important background why we have this ranking of visual variables. So this is the original one. We also tend to, this is the one adapted by Tamara Mansner for everything that is related to visualization except for electric shock. That's just because it's so much fun. And then here we have things like heaviness. So we tend to overestimate heaviness. We tend to overestimate taste. And then we tend to underestimate loudness and smell, for example. Okay, I'm going to do another experiment. How much longer is B than A? Twice. Everybody get it right. How much longer is B than A? 3 or 4? I heard mostly 4. Everybody got it right. How much steeper is A than B? I hear like many different things. 6, 3. The answer is about 4 times. So we can see that way less consensus on how much steeper A than B is. How much larger is B than A? 3, 4, twice, 6. Again, a lot of variation. It's about 5 times as big. How much bigger is B than A? 3, 4, 2 times, with the caveat by diameter. So if you look at the bubble, what do you mean? Do you mean diameter or do you mean area? And that's a common problem. You should always, if you do that, you should always use area. You should never use diameter because we perceive the area here. So this is twice the diameter, but means 4 times the area. How much larger is this now based on area, B than A? Twice. Here, most. 1.5, it's 3 times. How much darker is B than A? Twice as dark. How much darker is B than A? 5, 4, about 3 times. So the point of this is really to demonstrate to you, like empirically, that everybody got position right, right? Nobody, there was like, everybody said twice in like the same second, everybody said 4 times the same second when I used position. But then everything else was very, very varied. And there's this interesting game here that, again, another flash problem. So here, this is this eyeballing game that kind of like tells us a little bit about our weakness of our perceptual system for those things. So I'm trying to like make this a parallelogram, and oh, I'm actually quite wrong here again. Like I'm trying to find the midpoint of this line segment. This was good. I'm trying to bisect the angle. Well, not very good. Like you can see that there are certain things that we're good at, that's other things, like mark the point that is equidistant from all of the edges. This was pretty good. Here the center of the circle. So you can play around with this and find, like, again, all of these angle judgments, oh, this one was pretty good, but all of these angle judgments are hard for us. The point of convergence. Okay, so yeah, just this, you can play with this. It's quite interesting to see what we're good at and what not. So these things, they don't happen in an isolated setting. There are many other factors that affect accuracy of perception. Things like alignment, distractors, the distance, and then Hammond scales. So here, for example, we're using underlined bar charts, which is harder to judge for us than framed underlined bar charts. So here we have the bar chart A and the bar chart B, and we can simply make these comparisons in a better way, because we can also judge the proportions here between those ratios instead of just judging the length. And then if we have unframed but aligned, this is very easy for us to see that A is bigger than B. And then here we have a couple of distractors. So this here is harder to compare than this or this or this. Like here, this is actually, like these are actually of a different height, but even knowing that, it is hard for me to say which of those is the bigger one, right? Just because of the distance. So all of these things affect accuracy. There's many other factors. And then we're getting to this paper now. This is the original study by Cleveland and McGill from 1984, and they studied these things in these kind of like ecologically valid environments. And so they studied like which of these marks is easiest to perceive. And so this is not a replication study. Who has read the paper? Everybody should raise their hands, this is mandatory. Who wants to give a summary? No brave souls? Jen? Yes, okay, so let's rethink this a little bit. So they used Mechanical Turk to do a perceptual study like this. Who's ever heard of Mechanical Turk? A few people. Has anybody ever done any of these human intelligence tasks? Nobody has ever worked for Mechanical Turk? Has anybody ever run like a study like this? Or any other perceptual study? Okay, so what was the goal of this paper? What did they try to do?
The goal was to compare, well, to see if Mechanical Turk can be used in place of a user study.
Okay, yes. In place of a user study, can you be a little bit more specific?
Because Mechanical Turk is much cheaper than paying participants in user study.
Yes. Price is one argument, so like, okay, let's just recap, like in case anybody hasn't read the paper. So Mechanical Turk is this Amazon platform where you can give simple human intelligence tasks to a big group of people, and you pay them using micropayments. So, for example, for every task that you complete, you get like 5 or 10 or 20 cents. And you can actually leverage that for many different things. So it's been widely leveraged to create labeled data sets for computer vision, for example. Like ask people to to answer what do you see in this picture, and then they would say birds, leaves, what is the color of the picture, and so on. All of these things can be like done in these human intelligence tasks. And these guys, and this has been used also for studies, right? To get some kind of like surveys in to study human behavior. And these guys here did a rigorous evaluation of the suitability of the use of Mechanical Turk for perceptual studies targeted at visualization. Okay, and so what were the experiments that they ran? So, what did it compare?
One experiment was that there were two rectangles given and you had to tell which one is smaller than, by what percentage one is smaller than the other.
Yes, exactly. So they did like one study where they replicated the Cleveland-McGill study and then compared those rectangles, right? And they did most of these elements, but they also studied things that were not really popular. When Cleveland-McGill did this back in the 80s, they didn't really like use too many bubble charts and they didn't use tree maps. So they added those two techniques. And what did they find? You're welcome to look at the paper while you're giving an answer.
So results were similar to the earlier simulations, and then they found that position was the best, and angles were, the angles were not as good as areas.
Yes.
That's what they found.
So they replicated this study. They had very similar results, and so therefore they kind of like confirmed, on the one hand, that what Cleveland-McGill studied in the 80s is in fact correct, but they also confirmed that Amazon Mechanical Turk is a suitable tool to do these kinds of studies, right? And they did like a much larger experiment than Cleveland-McGill did. So why is there actually a concern about running this on Mechanical Turk versus in a lab study? What is the big difference?
The accuracy of the data you collect.
Exactly. And what influences the accuracy?
So like you're paying all these people to do it, and if they're just doing it for money, then they may not give it full attention.
Yes, like I can much better control for whether people are serious when they're in a lab setting. They might be intimidated by like doing completely stupid things if there is like supervisor there. So this is something that you have to control for. What else is a problem?
Technical equipment like displays for the computer.
Yes, exactly. So color is very tricky. You see this very often when I show you something on the screen. Like you can't properly see it because the color resolution of a projector like this isn't quite as good as my MacBook's screen here. So we have like this big variation in display technology, in resolution, in angle, in lighting conditions, in distance to the screen, in angle of the person to the screen. And I can also control for all of these variables very exactly in a laboratory study. And I can't really do that on a Mechanical Turk setting. And so what did they find? Was that a problem? So they showed that for these tasks where it's about position and area and so on, it was evidently not a problem, right? Because there's those that don't depend too much on the color. So what is the benefit of running this on Mechanical Turk compared to a lab study? Like when you run an experiment like that,
you can get more quantity.
Yes.
in the same time.
Yes, you can get like more people to do that. Other benefits of running this in Mechanical Turk.
Let's go.
Cost, faster, less cost.
Variation in the user,
Yes.
user taking the test.
Exactly. You wouldn't believe how well studied college undergraduates are and how badly studied, for example, like senior citizens are. We tend to like have a strong bias towards convenient samples because it's just so much easier to simply recruit 6 of your lab mates for a study than it is to go out and try to like replicate the population's number. Of course, Amazon Mechanical Turk comes with caveats too, but you can actually adjust the parameters of the demographics of the people that you want to find so that you can kind of sample the population. So we have a little bit more, this is called like ecological validity, right? we have a little bit more ecological validity with respect to our population, potentially. There's another aspect of ecological validity that we already touched upon. That would be the screen. Yeah, it's like the environment. Like people don't look at these visualizations in a controlled lab environment, right? They look at those visualizations on their various displays. So maybe any like recommendations that we make for practical visualization designs should take into account these variations. And so we shouldn't say, yes, there is a just noticeable difference between those gray shades in optimal viewing conditions. We should say we need to take care of the just noticeable difference for at least 98% of the population out there, right? And we can get these kinds of factors to work better with Amazon Mechanical Turk than we can in any way with any of these more controlled lab studies. Okay, so what other studies did they run?
The amount they paid the Turks?
What's that?
The amount that they paid the Turks?
So they did some kind of like, they always had two goals, right? They had this meta goal of evaluating how Mechanical Turk works. So what did they find for payment?
Like how much?
Well, no, what's their insight about payment?
Oh, that it will get the task done faster, but not better.
Yes. So that's a very important insight. Like if you need to get something done fast, you have to pay more, but it's not necessary that you actually that you get worse results if you're cheap. So that was an interesting point. What other thing is very important for accuracy?
Qualifying examples to make sure that they're actually
Exactly. So you have to have these qualifying examples because you will have some people that simply click through this without thinking, and you can disqualify them if you have any of those qualifying examples. And then in modern Mechanical Turk studies, we also run things like color blindness, pre-tests, and so on. So all of these things are important. Okay, so they also, like the second thing that they studied was this grid alpha aspect. So what was the idea here?
So they were trying to find out how the grid lines, so by adjusting the alpha values, so what alpha value is good so as to distinguish between the grid lines and background.
Exactly. So they were trying to find out what is a good alpha value, like how prominent do those grid lines have to be under various conditions. And they replicated a fairly recent laboratory study, like 1 year before they did this study. And again, they kind of replicated their results, but they had a little bit more variation, I would say. And this is, again, why is this not surprising that they had more variation here?
Because it depends on the system.
Yes.
Different display one.
Exactly. So size and so on is going to be more faithfully represented across multiple screens, whereas we have these systematic differences between operating systems, even in terms of how the alpha appears on different screens and so on. So there was a little bit more variation, but they concluded that you could still use this data in a, like, basically they saw the same trends, but they had some, like, a little bit more variation in that. Okay, so any comments about this paper? Did you find this a good paper? Anybody?
Yeah, I mean, it seems, I mean, like these kind of crowdsourcing things, they're so efficient now and so common, but it'd be easy just to kind of overlook the negative effects that they could have on our studies.
Yeah. So this is, crowdsourcing has been like, this is kind of the early phase, right? This is 7 years ago. And ever since, crowdsourcing has been increasingly popular to study perception in many different ways. So if you go to like a typical visualization conference nowadays, you would find like at least 20% of the paper use some kind of crowdsourcing. And the advantages are, of course, that it's easy to deploy, it's cheap, you get a lot of results, you can do runs quickly, and these systems are increasingly powerful. So they did actually two different things here. They gave just like image stimuli, but they also had an interactive stimuli for the second experiment, right? And so they had a little bit more control. And so you can also use this to evaluate interactive techniques. Okay, let me see whether there's anything else that I wanted to talk about. Yeah, so this is a figure from their paper. You can see that essentially the Cleveland-McGill results, they were very like similar to what they had. The ordering stays exactly the same. They have a little bit more variation in these error rates, these 95% confidence intervals for the log errors. And so here is like this ranking of these visual variables for these quantitative ordinal nominal data sets by like another ranking by decreasing suitability. And this is just to emphasize again that position here is consistently at the top. Yeah, I think we've talked plenty about this. So now I kind of like the last thing that I wanted to talk about today is the separability of attributes. So I kind of alluded to that at the beginning, that we have multiple visual variables. So we can, for example, combine position with hue, and these are fully separable. These are kind of like independent of each other to some degree. Then I can add size, but I'm starting to notice some interference, right? The color of this little bubble is not as obviously perceivable as the color of this big bubble. And obviously, if I went into the extremes and make this smaller and smaller, the hue is going to be harder to, and also the position is going to be harder to spot. If I start to modify width and height, then I have quite significant interference. So these are not independent anymore. And then if I, for example, took the color channel and encoded red, green, and blue separately as 3 data values, we have major interference. So this is like, we cannot do that. We have these different aspects, like of a color, and like this represents all of the data conceptually, but it's simply not, we cannot separate them in our heads. We would have to really think about this, and then this is not the point of visualization, obviously. Okay, so this concludes the lecture on marks and channels, and then I'll see you guys again on Tuesday for a deep dive into D3. Can you?
Yeah, I can. Okay, so just real quick, you guys are using Slack a lot for homeworks, and that's great. You want to be very careful with posting too much code. There's a few examples where we've had to delete the message, so I know it's just a screenshot of your constructor. The moment you put it up there, someone else can use it. It's not your fault, but then it's definitely plagiarism, so be careful with that. And the other thing is, for those of you who have been using Slack, you've probably noticed that the messages get all mixed up if 2 people are asking at the same time. So the way we're going to do that is, once you ask a message, all of the answers and discussion is going to go into a thread. And if you want to answer, just put, there's a little message bubble, and you say start thread, so that the only thing we're going to see is the questions on the main channel, and all the discussions are in threads. So just try and remember to do that to keep it a little more organized.
Okay, great. So see you guys Tuesday.